Hello, everyone. I'm really glad to see you all here this afternoon. I know it's been a long and busy day, so I really appreciate you coming here. My name is Mykyta Protsenko. I'm a software engineer. I worked in Netflix. I work in platform experience team. And my job is basically making sure all other engineers have tools and best practices so they can do their job without unnecessary pain. Today I'm going to discuss the best practices and methods of reducing the pain of managing infrastructure. Before I begin, I have a question for you though. How many software developers do we have in the room? Please raise your hand if you write the code for a living. Okay, a lot of people. And how many people from operations do we have here? If you SRE, system administrator, I see a few hands, and it's good to see you all here because this talk, it actually concerns both sides. Has anyone faced a situation like, I really need to provision a new load balancer. Can you please help me with that? I'm sorry, we're really busy investigating a networking issue right now. Can you please file a ticket in Jira and come back in a couple of days? We'll figure this out. And it doesn't matter which side of this conversation you're on. The whole situation hurts. And I can feel that pain because I was there. I was in issues. A few years ago, I was working in a startup. And the startup was quite successful. By the time I joined it, they realized the monolith application they were writing, it wasn't going to scale. So the team I was in, it was tasked with splitting this monolith into multiple microservices. I bet a lot of you can relate. So you probably already know that one microservice may require a bunch of infrastructure resources to be provisioned. It needs security groups, it needs auto-scaling groups, it needs databases, it needs load balancers, everything, you name it. In my experience, one real-life microservice may require about a dozen of different infrastructure resources on average. So when we have 10 microservices, we're talking about hundreds of different infrastructure resources. If we have several environments, test stage and production, it's even worse if we have hundreds or thousands of microservices. I don't even want to go there. Of course, we were a startup and we tried provisioning everything manually at the beginning. Let's do it now, let's automate it later, and of course, we failed miserably. Because the ratio of operations to developers in my team, it varied around 1:5 to 1:7. There was just no way we could have pulled this off in the long run. We realized that we needed to automate the whole flow, the whole process of provisioning infrastructure, not just writing some scripts. We needed to build the whole deployment pipeline, and we also understood that it required a cultural shift because there were just not enough people in operations to do everything. Operations and developers, they had to share at least some of the work. And this is exactly the topic of this talk. Which core principles we can use that will help you to adopt infrastructure as code? Which tools we can use to empower the developers, and how do we make sure that developers don't break everything? Because we developers will like to move fast and break things. And we're going to go through technologies and recipes you can try and take home. We'll cover practices that can make implementing infrastructure as code easier, and we are going to try all these solutions in a demo to make sure that they actually work and we don't just wave our hands here. Before continuing though, let's define some terms. What is infrastructure? What do we mean by that? 15 years ago, it was obvious. If we discussed infrastructure, we were probably discussing some server racks, some network switches, probably tons of cables. We could say then that infrastructure is a bunch of physical and software resources that we need to support our code, to support our services. But now we're working with cloud services. We don't actually care about the hardware in the data center. We know that it's going to break eventually, but we trust our cloud providers to take care of that so our services can keep running. And since we leave the job of maintaining the actual physical resources to our cloud providers, we can concentrate on software resources, on virtual machines, containers, networking rules, security rules. We can define our infrastructure and split it into 3 big groups. The first group is computing resources, like virtual machines, like containers. These are resources that developers care about the most because it's where our code gets executed. The next group is storage resources. It's everything from file storage to databases, NoSQL databases, relational databases. And finally, we have networking resources that help other resources to communicate, and that includes everything from security groups to load balancers. And yes, all these resources are software resources. It's software, it's code. It gets translated to CPU instructions, to ones and zeros. And there is no reason not to treat it differently from the other software we write. We already have best practices when it comes to creating reliable, maintainable software. For example, we don't store our code locally. We write our code and we check it into a version control system. We test our changes before deploying them to production. If we see somebody who wants to deploy to production without testing, we're like, stop, what are you doing? Put this code down and make 2 slow steps back. We have best practices when it comes to maintaining our services in production. We rely on logs, we rely on metrics to make sure that our code performs as expected. We use different methodologies to make sure that we can deliver reliable code fast. And we can totally reuse this knowledge for infrastructure as code. I bet you're familiar with 12-factor app methodology. You know, it's a set of best practices for developing software. It was made popular by Heroku, one of the cloud providers. And its goal is to reduce the effort to bootstrap a new service, reducing the development headache. And also to make our projects portable, to decouple them from concrete providers and concrete environments. And that is going to reduce operational headache. For our purposes, for looking at infrastructure as code, the most important parts of this methodology are code base, configuration, logs, and development production parity. Let's take a closer look at these practices. What is code base? What do we mean by saying code base? We want to make sure that all our infrastructure definitions are checked into a version control system. This way we can review the history of our changes. We're never going to lose changes. And our code base can become a single source of truth that we can use to provision multiple environments by applying externalized configuration. Configuration, we expose our configuration as environment variables because it's a universal and it's a secure approach that works on any operating system. When we provision our infrastructure, we generate logs, and we treat our logs as a stream of events that we redirect to a standard output, so the logs can become easily accessible for our next steps. This way, we can achieve development production parity. Because we have the same code base, we make sure that all our environments are identical. We get rid of the problems like, it worked on my box, or it worked in the test environment. Of course, there may be difference, like I need 2 instances in my test environment, and I need 50 instances in my production environment. But these differences are the differences in the configuration, not the code base. And if we apply all these principles, we get the system that is easy to launch, that it can be run anywhere. All you need is environment variables that are available to your code base, which gets executed, which generate logs, that they get straight into standard output as you execute your system, as you execute a process, and you can process the logs however you want. You can save them to a file, you can put them into Elasticsearch, you can grab them, you can make some decisions based on what you find in the log. And this kind of approach is really easy to integrate with your deployment pipeline. It doesn't matter if you have Travis CI, if you have Jenkins, if you have GitLab CI, Spinnaker, or something else. All these tools can work with shell commands. They can expose configuration as environment variables. They can treat logs that get supplied in the standard output. Speaking of configuration, though, I wanted to mention that Puppet, Chef, and similar tools are outside of the scope of this talk. Yes, you can use them to configure your infrastructure, especially computing infrastructure. But in cloud, it's much better to operate with immutable computing infrastructure. With immutable infrastructure, you can just create new resources for any change. If you need to update or install a package, you don't do an in-place patch. You just deploy a new batch of your containers or your services, and you just kill the old ones. The same applies to the rollback. You just deploy the new batch with the previous version, and you kill the existing one that obviously had an error or something. It makes your changes simple. It makes your system more stable because you don't have to deal with custom in-place patches anymore. You don't have to deal with discrepancies between environments. You don't have to worry about questions like, which version of glibc do I have in my test environment, and why is it different from my production, and how do I apply the patch to make them identical? And going back to my startup tale, yes, we wanted to have a mutable infrastructure and we wanted to treat our infrastructure as code. But APIs and CLIs, they were a no-go from the very beginning. Yes, you can create resources this way. Here you have an AWS CLI command to create a single load balancer. But what do you do if this load balancer, if the resource you're about to create exists already? Because if you run this command, it exists, you may get an error. Are you going to add another command to check its existence? Well, you can do that. What if there are differences that have to be fixed or reconciled? Do you need to add like 5 more calls to fix them? Well, you can do that as well. What if there are other resources that have to be reconfigured based on the changes you apply to this resource? It's just too many calls, that's just way too much code. That means that imperative tools and languages like CLIs or Java APIs just don't cut it. When you use imperative tools, you're saying, I want to change the state of the world this specific way, but if the actual state of the world is different from something you're expecting, you may get an error. You want to provision a load balancer, but it exists, you get an error. We realized that declarative approach works much better for infrastructure. With declarative approach, we can describe our infrastructure resources by saying, I want the state of the world to be like that. And then it's up to the tool itself to figure out what changes, what operations are needed to achieve that goal. If you need to provision a load balancer and it doesn't exist, it's going to be created. If it exists, but there are differences that have to be reconciled, they will be fixed. And if it exists already exactly the way you want it to be, nothing will happen. And you don't have to do anything special in all 3 cases, because declarative tools, they give us a benefit of idempotency. No matter how many times we execute them, they always leave our world in the same state each time. You don't need unique deployment scripts. You don't need to adjust them each time we change everything. If we need to make a change, we make a change in our declaration, and then declarative tools will take care of figuring everything out. So we started researching such tools. And first we found CloudFormation, and it worked. It actually worked. It let us describe our resources as code. We could use it as a single source of truth. We could put it into our version control system. But in my opinion, there was one problem. Let's take a look at this example. It's just a single DNS entry described as a CloudFormation resource. We have an entry type, we have a type to leave, we reference things like Route 53 and EC2 instance. But does it look simple or easy to read? I don't think so. And please don't get me wrong, I believe that CloudFormation is a great tool. It's great, it works. I just doesn't feel like it was written for humans. I feel it was written for robots. Angry robots that really hate humanity and all other living beings probably. So we kept searching, and then we discovered Terraform, and we were surprised by how human-friendly it was. This is the same DNS entry. It is written as a Terraform script. It's much easier to read because it's written for living beings and not angry robots. But even with this knowledge, when we know that Terraform is simpler, it's more friendly, we know that one DNS entry is not nearly enough for provisioning even a single microservice. So let's take a look at some of the resources that we actually need to provision a microservice to get it up and running. And let's see how we can apply 12-factor up principles to our infrastructure and what kind of the process we need to provision it. We're going to take the simplest possible hello world microservice. Here is the code. We have one controller, it just returns hello world. If you want to check out the rest, like the Docker file, the publishing logic, it can be found there in the GitHub repo if you want to check it out. And we're going to run this service using AWS Elastic Container Service. So we have our Terraform files here. This particular file defines our container parameters. In AWS language, it's called a task definition. We have our CPU quotas and memory quotas defined. We reference our container image. And we also need to define our Elastic Container Service. It's going to orchestrate our containers. It's going to make sure that we're running 2 copies of our container for redundancy. And you see that it references other resources like subnets, security groups. It also references load balancer. And if we check out load balancer definitions, we'll see that it references other subnets and other security groups and things like VPC. But if I'm a developer, I don't want to worry. I don't care about a VPC. I want to think about resources that are important to me, like my containers or my load balancers, maybe. On the other side, if I work in operations, I don't want developers to mess around with my core infrastructure resources, because if they make a mistake there, they can bring the whole system down. Imagine developers making a typo in a security group definition that is applied to public load balancer. One little typo, one character, and whole bunch of public load balancers, they become inaccessible in a second. We're looking at a very important problem here. We're looking at separating core infrastructure from project-level infrastructure. Fortunately, Terraform can help us with that. In Terraform, you can reference one project from another project. Let's review Terraform resources that we need for our core infrastructure. It's just a subset of them, of course. We see a few examples of the most basic resources like a VPC, some networking resources. Then we can tell Terraform how to store attributes of these resources as outputs, which attributes we want to export and where do we want to put them. Here we're saying we want to put them in S3 using these parameters, and then we can import these resources in your project level Terraform files. This way developers can know everything they want to know and not be afraid of breaking stuff. And operations, they can concentrate on maintaining the core infrastructure and the core tooling without worrying that developers will make a critical mistake. If developers break something, let me rephrase it. When developers break something, their mistakes will be related only to their own projects. It severely limits the blast radius in case something goes wrong. Let's now review the process that we can use to provision our infrastructure. I cheated a bit with a demo. I have to admit, I pre-recorded it because some of the operations in this demo, they may take a couple of minutes, and I just wanted to fast forward through them so we don't waste time. But the projects themselves, they are available on GitHub. You can check it out. You can try it yourself using your own AWS account if you want it. So let's take a look at the demo. We start with core infrastructure, of course. And since our infrastructure is code, the first thing we need is to actually go ahead and check out this code. We clone our project with our core infrastructure. And after it's done, we cd to the projects, to the actual directory with Terraform files in it. And then we are going to configure our project to expose configuration. Here, I'm saying I'm going to deploy it into US West 2. Why? Because it's the cheapest region. I didn't want to spend too much money. We need to do Terraform init commands, so Terraform can download all the plugins it needs to work with your specific cloud provider. In our case, it's AWS. And then we are going to do a dry run, because changing infrastructure, provisioning infrastructure is a serious business, and we want to review the list of changes we are about to make. So we can do it with Terraform plan command, and here we see we're about to add 13 different resources. We're not deleting anything, that works as expected. The resources in questions are things like VPCs, subnets, security groups. We can take a look at them, at their parameters, to make sure they look exactly the way we want them to look. And now we can make the next step and actually provision our infrastructure. And we can do it by running Terraform apply command. And please note these input equals false and auto-approve command line parameters. Why do I need them? Because if I'm running these commands in a headless environment, like in Jenkins Builder, I'm not going to have a console that can provide interactive input. So I'm going to just disable it to make everything uniform. So we have provisioned those resources, they were created, and here we can review the attributes of those resources that were exported and now are available to our project level infrastructure resources. And now we should repeat the same process for our project level resources. And we do basically the same thing over again. We check out the code, it's hello world, not the core infrastructure. We go to the directory with the files in it, we configure our project. Again, we're going to use the same cheapest region to provision anything. We're going to run Terraform command, Terraform init command to initialize the plugins for our cloud provider. And we are going to do Terraform plan to review the list of pending changes. And then we're going to going to actually provision all our infrastructure resources here. So we're about to create 6 resources, and the resources are things like task definitions that we have reviewed, things like Elastic Cloud Service. These are the resources we need to launch our microservice. So now let's provision them. Here's the part I actually fast-forwarded, because creating a load balancer, for some reasons, it takes a couple of minutes for application load balancers. I don't know why, I just didn't want to waste any time. So you see, like the time is actually fast forwarded here. And here we actually get the logs in standard output. So if we get an error, we can grab for it early, we can send a notification, we can do other actions. But here, okay, we see that our resources were added, but all we have now is the list of logs. And we want to make sure that things actually happen, that we don't just print things out. And we can do it by inspecting AWS console, right? We can visit this web page, we see we have this hello world service running, we can check the containers, we have 2 containers that are still pending, it takes a few seconds to get them launched. Okay, they have started, and now we can inspect a hello world service. We can see that it references the resources from core infrastructure like VPCs, subnets, and now we can check out the load balancer that it references. We can verify that our containers were registered with the target group of these load balancers. Yes, they are marked as healthy. They look good. And now we can check other load balancers attributes. The most important attribute for us is the actual name of load balancer, actual DNS entry, because we can actually copy it, we can proceed, copy paste it, and test our microservice with a simple curl command to make sure it actually works. And it works, it returns hello world. It's something to celebrate actually, because we just provisioned about 20 different resources in matters of minutes, and now we can repeat the same process in different environments without a fear of making a manual type or forgetting something or waiting for operations team to provision it for us, or without filing Jira tickets. Let's celebrate. Or is it too early to celebrate? Because after all, it's just day 1, and we're going to have days 2, days 3, and so on. We are going to face more maintenance tasks, more problem. The very first problem we are going to face is collaboration. Because we may have several developers working on the same project. One developer can make a change, check it in, deploy it, and other developers will check out their changes. They will make their own changes. Again, they will check it in. They are going to try deploying them. But if we just go ahead, we need to know which resources have been created, which changes have been deployed, so we don't step on each other's toes. And this problem is not limited to just developers. If you have several Jenkins builders, this problem will be applicable here as well, because if you provision something using Jenkins builder A, Jenkins builder B needs to know what happened before. To do his job, Terraform needs to keep the state of the world somewhere. By default, it keeps it locally in terraform.tf state file, and you might see it and be tempted to check it in. It's a file, right? Let's just put it into Git. But that would be wrong, because this file has sensitive information in it. If you have defined a database, this file is going to have a root password to this database, and you don't want to check in your root passwords. On top of that, this file has configuration baked into it, and you want to keep configuration and code base separate so we can easily reapply changes in configuration to existing code base or the other way around. Again, we have a fix for that. You saw already that Terraform has mechanism for storing attributes and the state of the world remotely. You can use different storage mechanisms. You can use console. You can store it in AWS S3 and so on. I recommend starting with S3 if you're working with AWS. First of all, it doesn't require any additional software. It's just there. Second, it supports versioning, so you can enable versioning on your bucket and restore your data, restore the state of the world if it becomes corrupted. And finally, the last but not the least, most of the teams, they can just fit into a free AWS tier, and free things are good in my opinion. Well, in Terraform state, you can describe your remote state similarly to other resources. You specify your backend type. You specify attributes to be used to store your remote states. Remember that command? In addition to initializing the provider's plugins, it also fetches the latest saved state of the world. It's just something to remember when you automate the whole flow. Now we actually can have the states, we have the steps that we can automate, we can use in the deployment pipeline. The first step is checking out the code. The code is where we define our infrastructure resources, our remote state configuration. We get the latest state of the world by running this command. Then we set up our configuration through environment variables, and we do a dry run. We review the list of pending changes before proceeding, because as we already know, changing infrastructure is a serious business. It's a good practice to make sure that our changes don't break anything accidentally. And finally, we can apply our changes. And we have nothing here but environment variables and shell commands. We can define a Jenkins pipeline or integrate these commands with any other deployment tool. And now we can do it for all our microservices, not just one. And we are going to have another problem here: copy, paste. Because it's tempting to just copy all our infrastructure definitions from one project to another. Well, let's just copy it, change some parameters and move on. But 2 months later, you may realize that you need to make a small change, like tweak a timeout for a load balancer health check. And you need to do it in 42 different projects, and maybe you have edited some of them so much that a simple search and replace doesn't work anymore. It's a bad situation to be in, yikes. It's a good thing, though, that we humans tend to be lazy. We like to do things once and then forget about them, like hiding them behind layers of abstractions and encapsulating them. Like, okay, I figured out what I need to do to provision this load balancer, which security groups I need, which subnets I need, where do I want to keep my access logs, and I don't want to figure out it again for my next one. I just want to say, create the one like the one I already created. In Terraform, we solve this problem with modules. Modules are reusable pieces of code that can be encapsulated, that can be treated as sub-projects. Inside, they are not different from your regular projects. You can still define Terraform resources in your models, and in addition, you can define inputs, variables, which will be provided by the actual project. Here we use service name and Docker image as inputs to create a new microservice. Then we can use these actual inputs to customize module resources. And we can use module multiple times in the same projects or in other different projects. And we can create multiple copies of all the module resources as needed. All you need to do is to provide input variables, and the rest of infrastructure complexity will be hidden. Now we can refactor our project using modules. If we reference a module, all we need to do is set up a name and a Docker image. The rest of complexity is hidden, so instead all these pesky definitions, all you have now is 5 lines of code literally, and you can provision it the same way using the same commands: Terraform init, Terraform plan, Terraform apply. But our maintenance problems, they do not end there. Because as your infrastructure evolves, as you make more changes, as you add more changes, you also add a risk of introducing a break-in change. For example, you can change an instance type of your EC2 box to make sure you have enough capacity. And the next thing you know, your old boxes are destroyed, but the new ones haven't been created yet. Or change the load balancer name. This change sounds harmless, right? It's just the name. What can possibly go wrong? But it also means that your old load balancer may be destroyed before new one is created. It may be not something that you have planned, it's just the way your cloud provider works. But it's bad, because you're going to face a downtime. The downtime may be brief, but you're still going to face it. It may be okay if your clients only use your system from 9 till 5, you can just deploy everything and 5:15. Unfortunately, in the modern world, we don't often have this luxury. Most of our systems are designed to run 24/7, so you gotta be extra careful. It means that during the dry run stage, you need to watch out for any accidental deletions. But sometimes the changes I mentioned are legitimate. You actually want to implement them, not to avoid them, but you still need to implement them without downtime. And there are several ways to approach that, to fix that. The first one is to define a life cycle constraint. For example, Terraform can provide create before destroy parameter. It makes sure that your new resources go live before old ones are decommissioned. The thing to watch out in this approach, though, is that you need to do the same thing, the same change for all resources that depend on that resources, on the resource you're fixing. For example, if you do this with your load balancer, you also need to do it with your Elastic Container Service that references this load balancer. And it may be not necessarily bad, you just need to understand the consequences. Another way we can fix it is by borrowing a page from a regular software deployment book. That is, by implementing green-blue deployments. It means that you're going to have 2 copies of your infrastructure, one green, one blue, one is taking traffic, and another one is just sitting idle. And when you deploy the change to the idle one. Then you can test it separately without affecting live users, and once you're sure it's working, after that, you can just redirect the traffic to it, effectively switching your environments. Then you can keep your old infrastructure around for a while, so you can fall back onto it if things go south. This approach is more complex because you need to manage traffic, and it's more costly. It costs more because you need to run 2 environments in parallel, at least for some amount of time, and pay for it. But it's also more safe because you have an old environment and you can roll your changes just by redirecting your traffic back. So choose the method that is better suited for your needs. And I would also like to note that everything we've seen before is not limited to AWS or Elastic Container Services or even Terraform. Maybe we're going to see another tool to provision cloud functions or manage neural nets. And maybe in 2 years, there's going to be a tool to manage quantum computers. I don't know, it doesn't mean that we should go back to this old way like, oh crap, let's do everything manually again. The same approach, the same principles can be applied to other tools. As long as you can describe your infrastructure in a declarative way, you can keep applying the same principles. Take, for example, Kubernetes. I bet a lot of you is using it already. You know, it lets you describe your container-based services declaratively. The definition, the declaration is YAML-based. It allows you to define most of the computing and networking resources for your microservices. Like you can define a load balancer, you can define a Kubernetes service, and you can totally apply 12-factor app methodology here as well. You can take this declarative description, you can modularize it, you can wrap it in a shell script to take care of substitutions. And I am oversimplifying things here. I need to make this disclaimer, because in a real life you probably want to use more advanced tool like a YAML templating tool, YTT, or even more advanced tool like Helm. But the result is going to be the same. You write your infrastructure definitions, you check them into your code base, and when you need to do an additional configuration to customize your resources, you can do it by exposing your configuration through environment variables. Kubernetes CLI, command line interface, it lets you to feed the data to it through shell pipes. And that means that you can create a script that will produce Kubernetes YAML definitions with all the resources that you can feed to kube control. You can check those definitions, those resources into your code base. You can apply externalized configuration, and you can build the same pipeline using Kubernetes now. We're still going to need to define our core infrastructure. In Google Cloud Problem, you're going to need to define your Google Kubernetes engine, like we do here, like we do here using Terraform. In AWS, you will need to set up Elastic Kubernetes service, but the approach is the same. You're separating core infrastructure from project-level infrastructure, and you limit the blast radius, and you automate your infrastructure provisioning. Your resources are now available in minutes instead of days. And if in a year or two we're going to get a new tool for quantum computers, we can still apply the same approach and build the same pipeline and get the same result. Repeatable, predictable, and fast deployments. That solves a lot of technical issues. But unfortunately, we're not limited to just technical issues. Human-related issues, people-related issues may be harder to notice, they may be harder to fix, but they can be more dangerous. For example, no matter how good your new tools are, people will resist changes, and that's natural. People are already familiar with the old ways. Old ways may be slow, they may be inefficient, but they're well known. They're predictable, and predictability is important. It means that your colleagues and your clients can synchronize their plans with you, even if they're not really happy about your speed, about your velocity. Being predictably slow and successful is still better than being an unpredictable failure. You can attack this problem from two different angles. The first approach is show, don't tell. If you choose a project, if you convert it to a new pipeline, it can actually prove that a new way can be much more efficient, especially if you bring numbers like provision resources manually, like provisioning 10 resources manually takes up to 4 minutes per resource. It means up to 40 minutes per environment. There is always going to be a risk of a manual typo, and automated provisioning runs in 4 minutes, it's 10 times faster, and it's much more secure, much more safe. That is significant improvement. That's important because we are social animals, because millions of years of evolution, they taught us to fear the unknown, because the one who ran away from the unknown usually survived. But if we see a paved path, if we see an example we can actually follow, that reduces this fear of the changes a lot. Another way of reducing the fear is limiting the scope of the changes. Easy automated deployments, they psychologically condition us to do smaller changes instead of big bang deployments. After all, if the change is easy, why don't deploy it now? Why wait? Let's deploy it. Let's take this small change and deploy it. And that reduces the risk because we are going to limit the scope of the deployment, we're going to limit the blast radius, and things are going to be so much easier to investigate if something goes wrong. And that means less risk. Less risk means less fear, and less fear means less resistance to changes. Next thing to address when we're dealing with humans is the learning curve. Any change that you're introducing means that people will have to invest their time and effort into learning new things, and they need motivation to do that. You might think, okay, they see 10x reduction in lead time, they see how easy it is to use infrastructure as code, how efficient it is. They shouldn't have any hesitations, any doubts. Well, on the one hand, you're right. You don't have to do a formal cost-benefit analysis to show that infrastructure as code saves time and effort. A simple project should be enough. Unfortunately, people have a lot on their hands already, and they can forget about this shiny new tool you showed them last week. You need to be ready to repeat your points again and again. You need to be ready to listen to your colleagues, to your users. You need to be ready to address their concerns, to invest into their education and plan accordingly. Basically, you need to be ready to invest into helping your colleagues. And the last, but not the least, there's going to be a tool interaction. New tools have to be installed on developers and deployment worker boxes, like a Jenkins builder. And these tools, all these tools, need to have the same version to avoid weird bugs because of the versioning discrepancies. How do we enforce version? We can just centralize all the tooling by forbidding developers to install the tools locally. Then we run everything using centralized executor like Jenkins builders. But I wouldn't recommend this approach. This way you increase the feedback loop time and developers is going to hate it. Because making change and testing it locally takes seconds. You make a change, you type it, you try it, it doesn't work, okay, something's broken, let's make another change, type it, try it, oh, it doesn't work. You repeat this cycle 20, 30 times, and finally you fix your issue and you move to the next one. And compare it to, you type your change, you commit it, you push your change, you wait for your builder to start a pipeline. Okay, there's going to be a link to this job. Okay, let's check the link. Okay, our job failed. Oh crap. Let's make this change again. This whole process of like one iteration of this process will take up to a minute or maybe two. And if you have like 20 or 30 of these iterations, like that's a huge productivity hit. So it's better to make sure that both the pipelines and developers have the identical tooling. We can achieve it by using Vagrant, which provides us with a pre-baked virtual machine where we can install all the tools we need with the right versions. It's a little bit heavy, but it does a trick. Or if you have an in-house package repository already, like a Debian repository, you can just distribute updates through it. Another option you can leverage is to use your existing build system. For example, if your developers use Gradle to build their Java project, they can add the plugin that can install the right Terraform version for them, and that will take care of the most common Terraform tasks transparently. And I have to make a disclaimer. I have to admit that's a shameless plug because I'm a contributor to this plugin, but you don't have to use exactly this plugin. However, using an existing build system to install and run the tooling is the approach that I would recommend, regardless of the tooling in question. Any tooling will come with some common tasks and some common settings. And if you encapsulate them, if you hide them using your build system extension mechanisms, you will reduce adoption friction. Developers will be happy to use something they're already familiar with. Be it Maven, be it Gradle, be it something else, all they need to do is to learn one more build command parameter, and that provides instance familiarity. Instead of learning a whole bunch of new tools and languages, they can start with something they're already familiar with, and they can learn more as they go, as they need. On top of that, if you extend your build system with your standard infrastructure provisioning processes, you gain more than just instance familiarity. You can enforce another best practice and create a set of abstractions, set of unified build commands for your infrastructure provisioning. That means that you're not going to be tightly coupled to your infrastructure tool. If for some reason you decide, oh, I'm not happy with Terraform, I want to go back to CloudFormation, you can do that. Or you can replace Terraform with another tool that does not exist yet. And you don't need to change your pipelines. And this is going to make your operations team very happy. And you don't have to worry about flexibility. Unified commands, they just provide a fixed set of entry points, and you can still implement the logic beside those entry points any way you want, using any declarative tool. Another part that makes sense to unify is monitoring. On the operation side, you may want to pay really close attention to monitoring. No matter how different your projects are, you want to use standard monitoring tools across all of them. This way you can reduce cognitive load, and it is especially valuable when you have an outage or investigation. You don't want to be like, oh, I have this project, where are the metrics for this project? And Datadog, cool, oh, it works, but we have another project, and where is the alerts for that project? In CloudWatch alerts, how do we match those together? So you need to make sure that you use unified login, metrics, and alerts for all your projects from get-go. It helps a lot when things go south. We mentioned a codebase as one of the tools in 12-factor app toolbox. Yes, we check all our code into the codebase, into a version control system, but the process of checking it in, it doesn't have to be a mess of free-for-all or Wild West. Developers, us, we already have good and established processes for keeping our code repository clean. The main idea is to keep the main branch clean and ready to be deployed at all times, and we have ways of achieving this. GitHub flow, GitLab flow, and other flows. The logic behind all these flows can be boiled down to the fact that actual work is performed in branches, and they are merged back to the main branch after testing and reviewing the changes. And the reviewing process, the process of reviewing the changes, provides an excellent opportunity to communicate, to share ideas. Fellow developers can share their ideas about the project itself because it's their domain area. And operations people can provide advice regarding the best infrastructure practices because they are experts at that. That can enable continuous integration. If we review each change we make, if we test it before deployment, then we can shift to automated CI or even automated CD pipelines. And that's a huge cultural shift. Once you realize that merging to your main branch and testing and deploying stuff is no longer painful, you can start doing it more often. You can start splitting your changes into smaller chunks. As we discussed before, that makes your deployments much safer. And finally, this approach also reduces the need in documentation. You are going to need runbooks, that goes without saying, but you are not going to need infrastructure documentation anymore. Your code should become your documentation, and a much better documentation than a Word file. You don't need to worry, have I updated that Word file about the last deployments? Did I have something to change there? You know that your code is up to date. You just check your main branch and you see that. All these practices, they can help you to deploy faster. Applying 12-factor up methodology to infrastructure as code, it prevents things like, oh, I'm sorry, we're busy, please file the ticket to make this infrastructure change and come back in like never. Your code now can be identical for all your environments. There are no more special snowflakes that were configured manually by the people who no longer work in your company, so everybody is just afraid of touching this special environment. You can get fast, safe, and repeatable deployments. And it doesn't matter which tool we use, Terraform, CloudFormation, Kubernetes, or something that hasn't been invented yet. All these practices, they work with any declarative tool. And here are the links to the tools that I mentioned or used during the talk. I would like to share them with you. And here's the list of the books that you may find useful if you want to learn more about infrastructure as code. And here's the rest of the links. Check them out if you want to see the slides or if you want to try the demo source code yourself. Or if you want to reach out to me on Twitter, I would like to hear from you. Hopefully now we can go home and make the process of our infrastructure management less painful. Thank you all for coming here. It was a pleasure to see you. Now we have time for 1 or 2 questions, I believe.
Yeah, hello. Thanks for the presentation. Can you please go back to the Terraform backend slide? Terraform backend slide.
Okay.
I'd like to ask a chicken and egg question.
Yep.
I think you know where I'm going with this.
Okay, I'm guessing. Like separating core infrastructure from project level infrastructure? Okay, yep. We have this GCP.
No. The Terraform backend, where you specify S3 as a storage
okay,
engine.
Yeah, sure. That's going to be a lot of clicking back.
Yeah.
Okay, here it is.
So how do you solve the chicken and egg problem? Because in the real world, what you want to have is a bucket provisioned automatically for you. You want to enable versioning. You want security. You want encryption at rest. So you want to provision AWS KMS key for that bucket to encrypt that file that you are going. You want to create a special security group that only your CI tool can have access to that Terraform state, and your developers cannot have access to that state because it contains sensitive information. So how do you terraform the Terraform backend?
So there is a couple of ways you can approach them. The first way is like really stupid, but it still works. You can just create this one special bucket manually, right? It's just one-time thing. You create this bucket per environment, but that's while it works, it's not the nicest solution. So what you can do as well, you can actually have a separate Terraform project defining those buckets. The downside of this approach that the projects themselves are not going to be able to share the states remotely, but they actually don't need to because their job is very basic, provision the storage mechanism. The storage mechanism is not going to have any special magic that even the core infrastructure needs. The only thing that is needed is these setup parameters, and that's it.
Yeah, we actually solved this problem a bit differently. We use the same Terraform project, and we do multi-stage apply. So we run multiple applies. So first we declare this as a template with placeholders, let Terraform provision the infrastructure in AWS, provision resources in AWS, fill in those, and then run a second apply, init, and then apply. So that then your local state is moved back to the Terraform.
That's a bigger problem because this problem is not limited to just S3 buckets. Yeah. Any remote any remote storage is going to have this kind of issue. And unfortunately, there is no one solution fits all approach because some of the storage mechanisms that they have version and security groups that have to be enabled. It is more complex, and like multi-stage applies can help with that. Other tools like HashiCorp tool, I forgot the name, to actually manage Terraform state centralized in a centralized way. With it, you can avoid this problem, but then you have to pay HashiCorp money to manage that state for you. So yeah, there are trade-offs. There is no silver bullet for that.
Yeah, and you run into the same issue with, for example, provisioning a database. Because in Terraform, you have this provider block, and the provider block, at least for PostgreSQL database, it doesn't support dynamic values. So you have to have static values in there, like database name, database port, because when you run Terraform init, it will actually try to check the connection to the database.
That's true. That's true.
And again, we have to come up with our in-house solution for that with ordered multi-stage provisioning. So basically, we created our own wrapper on top of Terraform.
That actually can be solved. Oh no, well. I guess you're right, but we can discuss it later because I guess we are out of time. We can probably have one more question if our volunteers will allow us.
Hi, Gil from AppsFlyer here. So, where do you draw the line between the things that developers should get and should have to understand in order to use your tools, and where do we tell them, okay, this is just the operations or infrastructure territory? Because for example, what I did was I used existing templates for Terraform, and what I did is create a Jenkins job that automatically populates them with a bit of logic around reactive parameters and things like that. And what I found was that on one hand, they all want the power of typing in all the things, but they expect us to automatically complete that for them should they not know. So there's there's the spectrum between what the infrastructure people know and want to give access to and what the developers actually understand. So I would like to know, how would you resolve that conflict?
That's a great question. I believe first of all, the first question is about what is safe for developers to touch, right? That basically defines a lot. So, as I said, you probably don't want developers to mess out with stuff that can affect other services accidentally without developers realizing them. But I would actually rephrase the question. I would approach this problem from another angle. Because yes, you're right, most of the developers, they don't want to dig into implementation details of infrastructure unless they absolutely have to. They just want to supply several parameters, and even for those, they want to have reasonable defaults. For example, in Netflix, we have a new tool to bootstrap a lot of such things. However, the question I would like to ask myself is how developers get all the information they need if they need it. Because in my experience, they start I'm a developer. I want to start worrying about infrastructure when something goes wrong. And when something goes wrong, then I want to see what exactly is related to my project, which resources my project uses or created before, what state are they in? So the question is, how do we display this information? How do we bring this information to users so the developer doesn't have to dig through tons of documentation or code? How do we supply those logs to them? How do we provide maybe some shortcuts? And that is a question, in my opinion, it's more a question about ergonomics. Like, how do we make this data accessible? So I guess we are out of time according to this timer. If you want to catch me, I'm here. I would love to talk to you folks, and thank you all for coming.
Thank you.